So in my talk, I'll be talking about word embedding, language model, and the deep learning, the trend, what we are currently experiencing over the NLP world. So I started with a saga of these three gentlemen who actually made this possible to the new world: Bengio, Hinton, and Lecom. But today's language model like Bird, GPT, Excel, etc., we did not reach out here by just doing simple experiments. We started long back. We started in the beginning of 60s, and then there are a lot of steps we reach out here. So what I understand and come across most of the young staff who join us and etc. So they don't know the backward history. They only know okay Word2Vec and the dimension is 300. So they don't know how Word2Vec came, why Word2Vec, and how things are there. So let us start at the very basic. I used to teach this, whole section in my NLP class when I used to teach in Triple IT. So I just, wrap it up for the 1.5 hour. So let us, start with the basics. So, well, machine does not understand language, and that's the problem with the NLP.
Sorry for interrupt. Actually, sir, if you need, we have already disabled the chat box. If you need, we can enable the chat box, or we can take the questions through the raise your hand. So it is up to you how you feel to take the questions from the participant.
Yeah, you can enable the chat box. If people have question in this slide, if we waiting for the last, they might lost.
Okay.
Sure. Okay. So machine does not understand language. Human language is pretty complex. So machine understand numbers. So transferring language to numbers are the preliminary thing we the community did it long before when we generated ASCII or Unicode and so on. But there are a lot of dissimilarities or kind of pattern in the language, and people trying to understand using a lot of mathematical methods during the early 60s. So what is that? Well, can we understand words and their occurrences? Well, what is the basic unit of language? I mean, we can even argue, we can go deeper into word, we can break it down, root and suffix and prefix and so on. But let us talk about word, and word has a particular frequency and occurrence order. So what is that? So can you understand that? So there are two very significant law came out in early 60s and mid 60s called Gibbs law and Hicks law. So if we understand Gibbs law, we can easily understand Hicks law. So what is Gibbs law? So I can talk about it in longer way, but I just brought in one video. Maybe that is more dramatic than my presentation would be. So just have a look. It's a longer video. It's a 20 minute. I will not play the 20 minute. I will possibly play for 1.5 minutes or 2 minutes. Just have a look, and then again we'll talk.
Hey, Vsauce, Michael here. About 6% of everything you say and read and write is the. The is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are the of and to. A in is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on, all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line, a power law. This phenomenon is called Zipf's law. And it doesn't only apply to English. It also applies to other languages like, well, all of them. Even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this. According to wordcount.org, which ranks words as found in the British National Corpus, sauce is the 5,555th most common English word. Now, here is a list of how many times every word on Wikipedia and in the entire Gutenberg corpus of tens of thousands of public domain books shows up. The most used word, the, shows up about 181 million times. Knowing these two things, we can estimate that the word sauce should appear about 30,000 times on Wikipedia and Gutenberg combined. And it pretty much does. What gives? The world is chaotic. Things are distributed in myriads of ways, not just power laws, and language is personal, intentional, idiosyncratic. What about the world and ourselves could cause such complex activities and behaviors to follow such a basic rule? We literally don't know. More than a century of research has yet to close the case. Moreover, Zipf's law doesn't just mysteriously describe word use. It's also found in...
Okay, so let me stop it here. So you can understand possibly now, so what distribution has a particular pattern in a text data or a corpus? So what to do with that? Can I do something with that? Well, we can do a lot of things. So now, with the inspiration from the Zipf's law, in mid-60s, the Hipps law came out. What is Hipps law? Well, before describing the mathematical equation, let me go here. Let's say you downloaded the whole Times of India for last 10 years. And you are trying to understand, okay, what are the word patterns? How many words are there in English language? Well, so now what you are trying to do, in the x-axis, you are trying to plot how many words you read. Let's say you read 1,000 words. And in the y-axis, you are trying to plot how many new words you encountered. So it will grow this way. After a certain point of time, the curve will tend to come a little flat, because you are not encountering that many new words every day. So things are getting common. Well, you might still get new words like named entities, like location's name, person name, and something of that sort, or new words which coined recently or something of that sort. But you are not really encountering a lot of words which have not been seen earlier. So how many words are good words? So this is called Zipf's law. So the equation could be seen as this way. So vocabulary V could be k n to the power beta. So now typically for English language, k is in the range of 10 to 100 and the beta is in the range of square root. So 0.4 to 0.6. Well, it depends on language. So if we look at Indian languages, are reasonably richer than English, because we have a lot of sandhis, we have agglutinations, we have gender, number, person dependent verb, we have a lot of other things. So the curve will be flattening maybe in the range of 1 lakh, 2 lakh. So typically for Hindi, that could be a range. And for other languages, let's say many other, let's say Dravidian languages, which has more agglutination than other languages in the northern part of India, so which has possibly more word forms. So this is Hipps law. So when you plot it, so people plot it, you can plot it as a raw, just as a count, or you can plot it as a kind of log graph. That's perfectly fine. If you do a log, you might encounter little more flat line, but that's Hipps law. So now, well, Zipf's law and Hipps law are fine. How can we use it for real purpose? That's okay. It describes certain functionality of language and word order and so on. Now let's say you are working for a search engine. Let's say either Google, or you are designing your own search engine for some purposes, for library, for any other thing. Now, if I ask you, what would be the index size? Because let's for Google. So according to Google statistics, they says every day they encounter 25% new word. Every day. That's the statistics they gave to us. Now, if it is so So what would be my index size in coming 2 years or in coming 1 year? Why I'm asking this? Because I have to put a lot more money to get my infrastructure ready, or to my data center ready. So according to some statistics, every 24 months, web size is getting double. So basically, we are getting a lot more content in the web, and Google has to like index everything. So if we know how many words we might encounter from a 20 billion total words, we might get a sense how much extra cost I have to bear to get my index ready by infrastructure. How much extra cloud, how much extra money I have to put. Well, okay, that gives us a sense. So that way it might be useful, but it's not the only way. It has a lot more implication towards future language model and word order. How? Let us see. Well, people started with one hot vector. What is one hot vector? It's very simple. Let's say you have a very limited vocabulary, like these three words, and you say, okay, this is my vector size. I just put one if this word occur. Otherwise, I just put zero. So you might encounter of having this kind of word vectors. You can also apply this to document level. You can have a vocabulary, and you can say, okay, if these words occur, you just put kind of one, otherwise zero. Now, what's the problem with this kind of vector space? Now, see, the problem with this vector space is if you try to calculate the distance between two vectors, you'll always get root 2. Because if you just pick any two random word vector and their distance is just root 2. So you are not getting any meaningful distribution of the word and their distances. So it's not useful. So what we can do instead? Then this gentleman called Fat is a British linguist who was also in India during very early days, 1920 and so on, as a professor in University of Punjab. He came up with this by looking at languages. He said, see, actually the similar words actually cohere, either sentence level or paragraph level. So for example, let us say, take an example. Let me hear from audience. Let's say I give you a word, you give me some other words which are very closely connected. Let's say car. What is coming into your mind? Audience, you can type in the chat box.
Yes, Sitanshu, just unmute yourself and just you can put your answer. Yes, SUV.
SUV, okay, fine. What else?
Yeah, Pankaj, you can unmute yourself.
Or you just chat, you don't have to talk. You just type in.
Automobile, vehicle, transportation.
Right, exactly. So I got my message. So if these words are connected between them, sorry for this, interruption. I don't know why this is coming, but anyways, so if we can get a word distribution which is telling me, okay, these words are connected, not by grammatical meaning, they are not synonyms, they are not antonyms, they are not homonym, or they are not hypernym, but they are somehow connected, and we know this by our cognition, the daily interaction with the world. So can we connect them automatically by mathematical methods? So people started looking at that. So the guy called Peter Turney came out with this idea in 90s. So can we apply PMI into or point-wise mutual information into words? So what is that? Very simple. Let's say shopping cart, angry bird, or light rain, strong tea, fast food. These are words which are kind of multi-word. They appear together, although individually they mean something else, but when they come together they mean something else. So if we apply some certain kind of mathematical theory, we can understand these words are tightly connected. So what is that? It's very simple. So simply we are trying to look how many times they are occurring together. So probability of x and y, how many times they occur together, and divide by the probability of x and probability of y. So basically how many times they appear individually. So if we apply this PMI, we might get this. My fellow letters, fellow citizen, at home, on earth, whatever. So their frequency or their individual occurrence is something of this sort. and bygone frequency, or they occur together, is something of this sort. And if we calculate PMI, so then this is the PMI. So the raw PMI is something, if we get higher PMI, they are highly related. If we are getting lower PMI, they are not related. So then a lot of things happen over then few years. People started coming with log distribution, which PMI is useful, positive PMI, negative PMI. Negative PMI is not useful. Sometimes it is useful, and so on and so forth. Now, people started talking about language models. So, what is language model? We can talk about a lot of things about language model, but language model is nothing but fill in the blanks problem we did in our school days. So if I ask you among these options, which will go in the first blanks and which will go in the second blank, what would be your answer? Audience? Just chat it.
No for the first and wait for the second.
Right. So, thanks for the muting. So, we are guessing this because we have and as a function word at the first place and but, which will actually reverse the whole connotation of the sentence in the next one. So we got some idea. And how we are guessing this? Because of we can look at the previous words and we are getting some sense. This will go here and this will go here. So can a machine do that? That's language model. Can you learn this? Well, I'm quite sure you have seen this smart compose in Gmail, or when you try to put something in your Google search, it actually auto predicts what you are going to type. This is something Google
Tani and Ken are actually
introduced.
Another is we use machine learning to start suggesting phrases for you as you type. All you need to do is to hit tab and keep auto completing.
This is language model. And also when you type something in your smartphone, that's also language model. So language model is everywhere. Sorry. Sorry, my Prezi got hanged and stopped. 1 minute. I'm here. I'm just reopening my Prezi. It's got just hanged. Sorry about that. Yeah, I'm here. You can see my screen. Yeah, good. Okay. So, fine. So Google auto-predict our search queries, our email, our mobile phone auto-predict what we type and so on. But see, language is so complex. So if you look at today's communication, either in Indian social media or mobile chats and WhatsApp and etc., we do not speak English. We speak English, right? So how many of you notice when you try to type English in your mobile phone, it does not give you good satisfactory result. So what we have been working on is called code mixing, and we are trying to develop language model on this. We call it Antaryami. Let me just show you very quickly.
Hello and welcome to the demonstration.
It's a 4-minute one. I cannot go for the whole one, but let me show you what we are trying to do.
Inspiration in building such a key. With the proliferation in the confluence of cultures, entities, like understand that in a code mixed language setting, there exists something called a switching point. Switching point is what is in Hindi. Again, we can see that the predictions are in Hindi. So if we select per as the next word, it's a Hindi word, but we can see the word login, which is again an English word. We select that from English to Hindi, switch again. We can see that we are getting Hindi words as the next word suggestion.
So probably you got the sense what we are trying to do. We are trying to solve the language mixing problem and the language modeling problem. So code mixing is not occurring only in Indian languages, but it is very common in Europe, US, and Canada. So Spanglish, Danglish, German English, Portuguese English, a lot more things are happening. When language are mixing together. So that's a new challenge. Now, very interesting phenomena. It's a piece of trivia, you can say. So, how fast we can type when we have, a good language model which is supporting our typing. So, if we think about QWERTY keyboard in a mobile device, QWERTY keyboard, I'm quite sure you understand, is a kind of BlackBerry kind of mobile phone. So, the world record says people type this text, this guy called Grace Park, almost 4.66 character per second. So that's the world record people, human being can achieve. So if you look at today's modern language model like Flexi, Swift keyboard for English, we can possibly reach out on an average, a normal human being possibly can type out 16 character per second or 15 character per second. So almost 4 times higher than the world record. So that's the kind of, speed of communication we can achieve. And if we look at Indian languages or kind of mixed languages, we are still less, maybe 8 or 9, not more than that. Sometimes it's also give us a lot of wrong prediction. Forget about that. Well, now what is language model and how we can formulate mathematically? So, and why we should talk about language model. So language model is a kind of holy grail to modern NLP. So if you look at spell correction to machine translation or part of speech or sentiment analysis and writing recognition or information retrieval, so language model is everywhere. So what we are trying to do in language model, we are trying to get the probability of a word sequence, word 1 to word m. Now, how we are trying to do that? So simply, given this equation, we are trying to calculate this. So what we are trying to calculate? We are trying to calculate the probability of each word, wi, where given the previous sequence, word 1 to word I minus 1. And if we make a summation of that, 1 to m, so that's the summation is giving us the probability of this whole sequence. So probability of each word at the location, and we are just calculating the summation of that. So how we can get the summation? So simply, how many times? So simply, if you remember the PMI1, so how many times the whole sequence, probably 1 to m occur or 1 to I occur, divided by 1 to I minus 1 occur. So that should be the probability, right? In a big corpus, let's say you download the whole Times of India or whole Wikipedia, and you are trying to calculate this. Now there is a problem here. The problem here is language is so dynamic, people can use it in millions of ways. So getting a longer sequence, the probability always coming lesser. For example, let's say we are trying to predict if water is so transparent that, and we are trying to predict what is the probability of the next word being the. Now see, if you try to calculate this probability from a Wikipedia corpus, you might get 0 because this particular sequence never occurred. So what we can do? So we can do a nice thing. We can break this problem into, probability chain problem. So you can say, no, we are not looking at the whole sequence at once. We are trying to see the previous one word or previous two word or possibly three words. I mean, we can vary that length. So it's an n-gram problem. So we can vary the length and you can see, okay, how long is good enough for me. So if you increase the n, you might get lesser probabilities because you may not see that particular sequence in your corpus ever. But if you squeeze down your n size, you might get a lot more variation, but you are not getting better probability. So it's a trade-off. So what should be the size of n? It depends on various things. It depends on language. It depends on domain. I mean, if you're English, but it is an English of Twitter, then it's a different thing. It's an English of Wikipedia, it's a different thing. It's an English of email communication, it's a different thing. So it depends on your corpus, your domain, and many other things. So why so? Why we are looking at previous two? I mean, inspired from the Markov chain model. Markov says, okay, fine, we can go in a longer story, but the basic assumption is when we have a longer dependency probability chain, we can simplify the problem by looking at the previous two occurrences or previous two instances, and we can still get similar result, not the exact one, but let's say similar result. So applying the Markov chain assumption, we are saying, okay, so we are trying to look at the previous two words. We are saying, okay, how many times this word and the previous word occur, divided by how many times the previous word occur. So what is the branching factor? So if the previous word is this, what would be the next word? So this probability will be divided by the total size of the vocabulary, because we will be getting a probability for all the words in the vocabulary, and whichever win by probability in the whole vocabulary, we say, okay, that word will be sitting in that place. So if we have a smaller corpus like this, let's say we have a small corpus of Baghdad restaurant, and we are trying to get the probability of words here. This part is actually taken from the Stanford lecture, but if you have seen this, wonderful. If you have not seen this, good to have a look. So now let's say we have this corpus and we are trying to develop this co-occurrence matrix, I1, 1, 2, and so on, and we are dividing by the single word I1, 2, and we are getting a probability. Now, so two things to see here. Number one, 1, 2 has a higher probability because that's the law of the language. But also at the same time, you can see a lot of zeros here, which is not a good. So if you think about a scale of Google, where you have billions of words in WEC, then if you create this, you are actually wasting space. It's not a good idea. And when you are trying to give use the results in nanoseconds, and you have to process this matrix every time for multiple things, it's not a good way. So what you can do better there, I'll come there. But this is the language model. So have you seen Google Ngram before? If it's a majority no, I can possibly go ahead. So Google Ngram is visible and downloadable from here. So let's say I'm just trying to search true words together, Trump and Modi together. It's not there. Can audience give me some words or two words? In chat. Audience, are you still there?
Audience, yeah, Mohammed Khan.
Mohammed Khan. Who is the gentleman?
Policy.
Okay, fine. So it's there.
Policy.
Sorry?
Policy.
Policy
Policy.
What is
Policy.
policy?
Policy decision making. Policy and decision, sorry.
Policy decision. Okay, it should be everywhere. So this is a kind of occurrence of policy decision in the overall Google corpus. Okay? But this is not the important part. The important part is this part or this corpus is actually downloadable. There was some link here. Download raw data. Yeah. So it is downloadable from here. So 1 gram, 2 gram, 5 gram, and so on. So the whole data set is downloadable. Each file is more than GB size. So you can see whether you can download this and want to use it for any of your purpose, or research or whatever. So it's freely available. So coming back to our discussion. So this is the language model in the 90s we got. Fine. So how to evaluate language model? I mean, fine, we calculate certain kind of probability. That's okay. But how do I know my language model is good or bad? It is working or not working? Because when we apply this, we need to know that. So there are two kinds of evaluation in language model. One is intrinsic, one is extrinsic. What is intrinsic? Intrinsic is, well, I don't want to use it for some purposes. I want to see whether it is good or bad. So that's intrinsic. So what is that? I'll come there. Extrinsic, what is extrinsic? Well, I do this language modeling and then apply it for certain purposes. Either next word prediction in my mobile phone, spelling correction, grammar correction, machine translation, pause tagging, sentiment analysis, whatever. So I apply this into those kind of tasks and see what is happening, whether I'm getting a good results or not. So if you look at today's world, like Word, GPT, and etc., they are being applied to multiple NLP tasks and they are being proven to be a good method by evaluation. Now let us see what is the intrinsic evaluation. Well, so now if you look at perplexity definition this way, or this is the analogy. So again, fill in the blanks. And let's say in the right side, you have a lot of options, mushroom, pepperoni, and so on. So now if I ask you what will go in the first one, you might choose something from the top two. And the third president of US, you might choose nothing because you have no option here, at least not visible. And then I saw A, you can see anything in the word. So see, when we design a language model for certain fill in the blanks, you might get a lot of options or definite options. For something you do not have a choice, and sometimes you have possibly everything to go there. So if we do this way, if we take an average, how likely, what is the confidence of the language model predicting the next word, we might get a sense. Okay, what is the capability of my language model in overall? So that's the definition of perplexity. So probability. So this is our language model definition. Forget about this one. I'll come there. So this is our language model definition, right? Probability of a word sequence, word 1 to word n. So now, if we want to take an average, we're not taking an average because it's a probability. We're just taking a root of n. So we have n words, root of n, and we are getting 1 by probability. And we know this is nothing but probability of wi in a whole sequence, and we are taking a summation I equal to 1 to n. And applying the Markov chain model or Markov chain assumption or Markov assumption, we say, okay, we are not looking at the whole sequence 1 to I minus 1, we are just looking at the previous word, wi minus 1. So this is my perplexity definition. So what I'm getting here, I'm getting a sense that on an average, in the whole sequence of my test corpus or test cases, what is the probability the system is giving me? So probability in a sense, what is the confidence? If it's a higher probability, then the confidence is higher. If it's a lower probability, the confidence is lower. Okay, so what I'm getting. So that's the definition of my perplexity. So how does it translate to, if you take a corpus and try to do a kind of n-gram language modeling, if you go to trigram, you might get lower number. So perplexity is lower. So when you read the perplexity overall, the lower number is better the higher number is, bad. So you are getting a better perplexity number if you use more graph. But if you continue to upgrade this and try to 4, 4 to 5, 5 to 6, you might lose it again. So there will be a sweet spot which is actually good for language. Now forget about that. Okay, fine. So we got this idea of language model. So how we can formulate language model and how it could be useful. Now, the two problems. If you remember that co-occurrence matrix, the problem was a lot of zeros. Why a lot of zeros? Because we have not seen a lot of words. And I also give you another example of saying Google is encountering 25% new word every day. So if we have a language model which is always giving me probability close to zero, it's not a good idea. So what we can do better? So the first idea came up with called smoothing. So this we already discussed. If we increase the n, we may get greater discrimination. We have a lower n or smaller n, we might get more reliability. So we have to find out a better n size when we are designing the language model. But if you look at modern language model like Word, GPT, etc., they are taking the whole sequence into consideration because they are using attention model. An attention model is a nice theory where you are giving a particular probability to a whole sequence when you have a whole sequence, and you are giving a particular probability to a word while predicting the next word. Well, but forget about that. So come to smoothing, come to the basic. Okay, so if we calculate the probability distribution, if you remember the Zipf's law, we'll be getting a Zip pattern, right? And we'll be having a lot of words which are almost closer to zero. Now, combining these two, what we learn from Zipf's law is this will be a Pareto optimal font. So there will be a Pareto optimal font here. But in real life, we may not get it every time because we have a lot of words which may not occur significant time. So if we try to smooth it up in a sense of probability distribution, how it may look like. So let us see the math first and then come back again in the analogy. So what we are trying to do. So we are trying to do a very simple thing. We are saying, okay, so see there are word sequences which never appear in my data set, in my training set. I never see those words to be sitting together. Okay, so when we might have this in the real life, in the test case, we cannot say the probability is zero. What we are saying? We are saying, no, let's say we have a smaller probability. Let's say we put 1. If this is 0, what we'll be getting here? We'll be getting 1 here. But see, we are disturbing the distribution of probability, right? If we are forcefully adding some number from the outside. So what we are doing, okay, we are trying to draw a balance here. We are saying, okay, divide it by the total number of vocabulary, which is p. Okay, so 1 by p, we are just adding here. So what essentially we are doing? We are essentially doing, this is the actual probability look like distribution. We are taking the, some probability stemming from the, higher probability guys and distributing it among here. So what we are essentially doing, we are just trying to establish the Pareto optimal font here. So that's called smoothing. So if we go by this, forget about that. What we are doing it here, if you remember that co-occurrence matrix, we are putting a lot of 1 here. So instead of 0, we have a lot of 1. And then again, 1 by p, basically we are getting small probability number instead of 0. And that gives us a better distribution in terms of language model. Now, you can do it on bigram, trigram, and many other things. And this is really useful. Now, this is not only the smoothing technique. There are a lot more. So if you look at the whole 90s, people worked out with various different kind of smoothing techniques, and one have advantage over other. I just remember possibly 15 kinds of smoothing technique I have seen altogether. So, and people show in different kind of corpus, different kind of application. This smoothing technique is better than that, and so on and so forth. So among those almost 15, possibly it's good to look at the top 3 or top 4. Laplace, additive, good. I mean, these are almost same, but there are certain difference. Good theory, measurement. So these are the top 4 smoothing technique, people videos. This is a link in my slide. You can go there, read about them, and see. So now, going further. Well, what's the problem? The problem is that we are still having a very large matrix, which are really, not processable in real life. Real life, in a sense, in a Google scale and the real time, because we have to produce answer in nanoseconds. So let me skip this video you possibly have seen. So this is the problem. What is the problem? So the problem is we have a larger data set, a huge one, and we are trying to get some particular document out based on our necessity. So that's information retrieval needed. So let me keep the whole story short here. Okay. So people came up with nice idea to understand the word and its significance in a given document or a sequence. So the DFIDF, the idea of DFIDF came in. So what is DFIDF? Given a word, how many times it occurs in a particular document. So that's DF, term frequency. What is IDF? Well, if we look at the part of speech theory of word, there are two kinds of words. One is open POS, one is closed POS. What is open POS? So typically noun, verb, adjective, adverb. So members in this POS category are never finite. You cannot make a dictionary which is complete for this POS category. There are always members which are unlimited in this category. But if you look at, on the contrary, the closed POS, preposition, postposition, conjunct and other things, which are finite for a language. So this open POS category is called the content word, and the closed POS category is actually the filler in a language. So if you take the noun, adjective, adverb of a sentence, of a paragraph, they are the content, and the other words are actually joining them to make a language. Okay, so those words which are not kind of content words, they appear everywhere, but they are not much meaningful. So how we can get mathematically, put them out or giving them lower probability while calculating something statistical. So word like to, and, the, and so on. So that's the idea of IDF, inverse document frequency. So in a given corpus in a sense, let's say for Wikipedia again. So given a word, how many times it occurs in the particular document versus how many times it occurs over all the documents. If a word occurs over all the documents so many times, then that word is not very, very meaningful for this particular document. So that's the idea of IDF. So I had an example. Yeah. So simply of this sort. Okay. Let's say this is an example from Shakespeare all work. So word like Calpurnia, named reason, etc., nouns, animals, Sunday, and etc., would be higher IDF because they appear only a particular document, whereas word like the will be almost appearing in all the documents, so their IDF would be close to 0. So if we counter EF and IDF together, we might get sense how words are connected to each other. So instead of joint probability of before smoothing and etc. we talked about, so can we use the IDF kind of situation? So people tried that out during this information retrieval era. I mean, the started era. So people also started looking at some other kind of measure. What is the other kind of measure? So correlation coefficient. This is very interesting one, and in a large corpus, people see this has a lot of values to consider for. So what is that? So for example, angry bird. So angry and bird possibly never co-appear together unless the actual game comes. Right? So people started talking about, because we never seen, I mean, at least I did not see any bird which is angry. Okay, so what is the concept? The concept here is, can we see how many times these two words occur at the document level? So for example, this is a row from my index table, let's say from Google. What is the TF-IDF of that particular word in the document 1, document 2, document 3, and so on? And if I consider this row as a vector, and words, what is the TF-IDF in this particular document series, and so on. So if I now try to calculate this equation, so this is my VA, basically the vector of the angry, and then mu A, the kind of median of this vector, and db minus mu b, and then we are getting the standard deviation of a and standard deviation of b. So what we are getting essentially here, how related these two vectors are by this simple mathematical equation, covariance and standard deviation of a and b. What we are getting, how words are co-appearing. And after learning this, if we apply this in a bigger set for information retrieval and many other things, people shown in their research papers during this time, when people have been trying out a lot of different methods, and people reported better accuracy and better performance in many terms. Well, now we were still in that problem of having a large vector size. Large vector size is still a problem, because if you think from this perspective, just think about this. If it's a Google scale, number of documents would be in astronomical numbers, in trillion or zillion. And if you think about the number of rows, that might be limited all the time. It depends on the vocabulary size of word in a particular language. So we are still not sure how to deal with the dimension of the vector. So what we can do? So the basic people tried with the matrix factorization technique, and later on people come up with Word2Vec, and that's possibly the bingo situation for the NLP world. So what is singular value decomposition? What we are trying to do, we are trying to break a bigger matrix into smaller pieces of matrix, and we are trying to understand the Latin space, how things are connected to each other. So what is that? So let's say this is the case. If we have a matrix, we are trying to break this matrix into U, sigma, and V transpose. So this is little complex to understand. For simplicity, I will not go much into mathematical details. Rather, I will try to give you the concept, how this works, and how to make some analogy from this. So what is this? So typically U is this matrix, which is kind of vertical. Sigma is a matrix which to be looked at diagonally, and V transpose is a kind of horizontal matrix to be looked at this way. What does it mean? Again, let's say this is for analogy. This is not the exact example. Huh? So analogy. What is analogy I'm bringing here? So let's say you are looking at Netflix, and let's say for the time being discussion, you have one Netflix account and you are sharing among 10 or 20 people. Or let's say you have the data of whole Netflix. Okay, sorry for that. Okay, now you are trying to understand who watched what. What is the pattern? And you have this. Okay, what is this? This is something the row wise is user, and user has given ratings to two particular movies like Matrix, Alien, Serenity, Casablanca, Emily, and so on. So what is their rating on this particular movie? Someone gave 1, 3, 4, 5, and so on. So now if you look at this particular matrix, what you can infer? You can infer possibly these guys in this smaller box, possibly if you think here. So these guys are basically sci-fi loving people. They are looking at Matrix, Alien, Serenity, and so on. But if you look at here, the people who watch Casablanca and Emily, they're basically romantic type of movie love. So this is a kind of pattern which can be visible in human eyes. But can we do certain kind of matrix factorization which can automatically give me this kind of relation in the matrix? And that's the whole essence of doing the singular value decomposition. So what is decomposition here? So decomposition here is we are breaking it down into 3 matrices. That's the decomposition. Why singular value? Now singular value is, so if you look at this matrix, which is diagonally giving you some numbers, which is telling you what is the significance of this particular row. So that is 12.4. I mean, if you ask me what is the significance of this number, is it a range of 0 to 100? I mean, there is nothing of that sort. Okay, it's just a number which has to be seen in comparative ways. Okay, so this is the significance of this column, and this is the significance of this row. And now, what is 9.5? That is the significance of this particular column, and that is the significance of this particular row. So now, again, let me go back go to little more slides. Huh. So actually, if you apply singular value decomposition, you might get this kind of three matrices initially, which is U, this is sigma, and this is V transpose. So this is U matrix, which is typically called about user matrix. If you think about the Netflix situation, this is the concept matrix, and this is the sigma matrix, which is giving you the kind of uh, importance to the particular column or to the particular row. So now, see, the problem we encounter here and we come from is we have to reduce down the dimension of the matrices or the vector so that we can process it so quickly and we can do some computation very quickly. So what we learn from here, this column and this vector or this row has not much significance compared to other two, the 12.4, 9.5. So if we drop this down, and if we drop this down, ideally we should get similar results. So what happens when we have a matrix of Google scale? So number of columns is in zillion or trillion, and number of rows are in somehow 80 to 90,000 of that range. So now if we apply singular value decomposition, we'll be getting three matrices U, sigma, and V, and then we are saying okay, we do not need all the dimensions. We will look at the top 3 or 4 dimensions, let's say. And if we look at top 3 or 4 dimension, all the other dimension will be dropped. And we will be using this reduced matrices to process the further things. What is that? Let me go to an example, possibly you can understand that. Then I will come back here. Okay. Now let's say a very simple example of information retrieval. So what information retrieval problem we have? Let's say we have this 3 documents. Hopefully you can read my screen. If you don't, I make it bigger. Okay. So I have 3 documents, D1, D2, and D3, and this is kind of collection of my document. Then I'm trying to make a query in this document set. What is my query? Gold, silver, truck. Okay. Shipment of gold damaged in a fire, delivery of silver arrived in a silver truck, shipment of gold arrived in a truck. These are my document set. So now, by basic formulation of information retrieval, what we'll do? We'll make a one hot vector of query and document both. Right? So we have a vocabulary size of this. This is my total vocabulary. What we are doing here? We are just putting 1 and 0. If this particular word appear in my document, then 1, otherwise 0. So we got this vector, this is for document 1. We got this vector for document 2. We got this vector for document 3. We are done. So these are my 3 documents. And also we get a query vector like this, 0, 1. So basically 1, 1, 1, 3 words, 1, 1, 1. Okay, so I got vectorified query and all the documents. Now what I need to do? I need to calculate kind of similarity of my query with the document vector, either by cosine similarity, Jacob coefficient, or whatever. Some kind of similarity measure I have to do. Now, the problem here is, although this is a tiny problem, but if you think about this, number of words would be huge. And if you think about number of documents, that is also huge. So what we can do, we can apply singular value decomposition on this. So what we have? We are just breaking it down, the whole matrix, into U, sigma, and V transpose. Now if you look at sigma, forget about U and V for the time being, you see we are getting this column is of importance 4 point something, this column is of importance of 2 point something, and this column, the last one, is of importance of 1.27. And if we do V transpose, then we are saying this row is of importance of 4, this row is of importance of 2 point something, and this row is of importance of 1.27. So we got these 3 vectors, U, sigma, and V transpose. So if we want to squeeze it down, we are saying, okay, let us take the top 2 significant dimensions. So this and this, we just drop this column, we just drop this column. So we are saying, okay, we are dropping down the irrelevant dimension. We get this sigma nu, and we get this u nu. We just drop this dimension, and we just drop this dimension. Okay. Now with this, if I process the similarity between the query and the document, so this U matrix, we'll get something of this results. So how similar they are, and also we applied the singular value decomposition on this query vector as well, and we got this as a 2-dimension of this. So now we are applying the similarity, basically cosine similarity, simply how it is being calculated. I don't have to repeat all this mathematical equation, possibly you understand. This simple cosine similarity. Now if we apply this, now you look at the example again, and I would like to hear from the audience in terms of chat or voice, whatever. So if this query is given, gold, silver truck, you look at this documents, what do you think? What should be the ranking of this document? Which one should come first? Which one should come second? Which one should come third?
Yes, Prabhat, you can unmute yourself. Yeah, Rakesh. Yeah, Raj, you can unmute.
Please write it down in chat if you.
Then D3 and D1.
D3?
So for D2, then D3 and D1.
D2, D3 and D1. Okay. Anybody else? Any other answer possibly?
Yeah, Abhinav, Anand, you can unmute.
Yes, sir. It will be serially D1, D2, D3.
So now, let us see the results and answer. If we apply this, we are saying getting D2, D3 and D1. So that's the answer actually. So now, what we need to see is, come back here. If you do not do this singular value decomposition and do not get the squeeze down matrices, if we just apply these matrices 1, 0 and simply apply cosine similarity, you will still get that result, D2, D3 and D1. But if you squeeze down this and do the singular value decomposition and take the squeeze matrices like this U and do the composition, do the calculation, you still get the same answer, D2, D3 and D1. And that was a big situation for the information retrieval community. Why? You might not get a sense from these tiny values and tiny matrices, but just think about the Kobo scale again. You have zillions documents in the column. You have millions of rows in your matrix, and when you squeeze it down to top 100 dimension or top 200 dimension, and you are able to calculate and getting the same results in nanoseconds, you can now serve people in real time. That was a great development in the NLP world and in the way of this matrix factorization, singular value decomposition. So that's a nice theory. Now, how to do singular value decomposition, how to break it down, and so on. That's another class I used to take. That's a longer one. I cannot do it here. That needs at least 2 more classes. So that is the motivation for even Nikolov when he was a PhD student in Czech. So when he come up with the idea of king, queen, and etc., that's actually motivated from the basic of singular value decomposition. Now again, in retrospect, from one hot vector to PMI to DFIDF to correlation coefficient, we come across to SVD. Basically, now we hit the latent semantic space understanding, and which is actually the father of word embedding. So if you want to know how to calculate SVD and etc., possibly many of you already know, because many people are already come from mechanical electrical background, and singular value decomposition is a very well-known technique in those sciences, and they apply it in many other spaces. If you don't, these are the links. You can go there, and there are lots of dozens of nowadays lectures available online. You can look at how to calculate SPT. But the important here is SPT becomes very important for the NLP world after this. Now, I just take a pause here before I jump into the next step. We have already spent 1 hour. We have half an hour to go. So I would like to open it up to the audience and to the house. Any discussion, comment, anything we can discuss for 5 minutes. Just feel free to talk.
Does anybody want to say anything? Any questions?
Yeah, Akash. You can unmute yourself, Akash.
Hello. Hi, sir.
Hello.
So actually wanted to know whether cosine similarity and SVD are still used in the NLP world, or have they become kind of stale and we have moved toward evidence?
Well, cosine, the answer is complex. The answer is yes, they are still being used. Number one. So cosine similarity is still being used when you have a vector space and etc. to calculate, because it is so easy to implement, but still elegant and useful. ASPD, yes, it is still being used. See, Word2Vec and other kind of technique works really well if you have a large amount of data. Largeness is large, huge GB of data. But in real life, see, I'm in an industry and I'm solving a lot of real life problems for various companies, various other organizations. And when they don't have actually, large amount of data. But if you don't have large amount of data, you are still trying to apply those kind of neural techniques, it fails. But SVD, again, so strong and so useful, it is really useful even today.
Okay.
There's a nice paper. It gives me a nice, analogy to understand. So there's a nice paper in 2006 SCM. I just don't remember the exact name of the paper or the authors. Probably somebody from Israel Mathematical Institute or so. So they showed a nice analogy between Word2Vec and singular value decomposition. They have shown if you really apply singular value decomposition on a large data set, you can still something similar vectors like Word2Vec does. So in a sense, although the paths are different, but both of them lead to Rome. It's the same thing. They reach out in a different direction.
Okay.
Any other question, participants? Kindly raise your hand.
No more question?
Just Ravi, ask Ravi, unmute yourself and ask question. Hello, Ravi.
Hello.
Yeah, you can ask.
Sir. Sir, what is the difference between human intelligence and natural language processing, sir? Human interaction.
That's a tough one. Well, human intelligence,
No, sir. Human interaction in artificial intelligence is there no?
Let me give the answer in twofold. One is philosophy, one is image. Okay, so James Watson, who discovered the human DNA and got the Nobel Prize from Harvard. Okay, he said a nice thing. See, how human brain functions, we have no idea. We have the idea about the hardware, but we have no idea about the operating system. That's the philosophy. So we don't know, okay, how human brain really functions. We have some idea, we don't know. Okay, now what about applicability? Well, applicability comes from the engineering perspective, not science, engineering. So engineering is, we have something to apply. We have some use case. We have some problem to solve, either machine translation, sentiment analysis, political analysis on Twitter, or whatever. We have certain problem to solve, and we go back and try to understand how language appears, how we can formulate the problem, how we can solve it effectively. So that's the difference between human intelligence or human interaction versus today's NLP. Now, whether we are coming closer to human intelligence, well, yes. In recent times, GPT, BERT, and many big language models have shown significant development in writing documents which exactly look like human being written and so on. So, a lot of development. But are we still closer? Well, maybe not, because if you look at complex things like metaphor, understanding, sarcasm, twisted language, hate speech, fake news, these are unsolved. So that's the way possibly science works. We solve something, we look for the next, we try to solve the next.
Yes, Prabhat. Unmute yourself.
And AI machines interact with the human.
Right. So is it a question or statement?
Sorry?
It's a question or statement? I don't understand.
Sorry, sir, question. How I just want to know how they interact with the human. So also they have the language converter or anything just like that.
Okay. So language, how interact. So are you talking about chatbots, or you are talking about that kind of thing, or you are talking about something else?
Chatbot.
Okay. So chatbots, if you look at today's chatbot, what we do is simply we break it down to kind of speech act or dialogue act. So when we talk to, when we are doing interactions, right? So you are asking the question, I'm answering, right? So we have kind of dialogue act. So we ask question, we say thank you, we raise we make a statement, we say yes or no, we say thank you, a lot of things we say. And according to the other user also react to that with a certain dialogue act. So that's the basic of dialogue. So when chatbots are being built, first whatever people say and whatever machines say, those being classified into particular dialogue acts. Then the machine understand what they're trying to ask or say. Accordingly, they generate the response. So that's the way typical chatbot works. Now, what is the flow of this dialogue act? There is no certain rule, because human beings are trained to learn this from their whole life. So what a lot of companies are nowadays doing, they are getting a lot of huge corpus from various sources. Recently, in the last Google in the sense that their annual meet from Google, so they released a big corpus and a new chatbot which are trained on a million data set and so on. So which can automatically learn. If you also look at GPT also do the same thing. So,
sir, it means that sorry, sir, but it means that they will learn from real world experiences, right?
Right.
Okay. That was the thing I just want to know. Thank you, sir.
Sure.
I think, sir, you can continue. If some questions are still there, we can take at the end.
Okay. So we have almost 70 minutes to go.
Yes.
I cannot complete the whole thing. I mean, there is no completion at all, because a lot of things to talk about. But what I want to come back and talk here. See, when we discuss about the co-occurrence matrix generated from a bigger corpus, we get a lot of words and their kind of relatedness to the other words. And that's the beauty of any language model or Word2Vec. But there's a catch here. There's a limitation. What is the limitation? So, for example, words like human and user. If you look at this matrix, human and user, these are two such words which will never co-appear because they are kind of mutually exclusive. When human appear, user will not appear. When user appear, the other word will not appear. So, are we getting a good sense of distribution in the vector space so that we understand these two words are very, very nearby? Similarly, if you look at machine and system, these are two words, again, mutually exclusive, which never co-appear. So, are we getting a reasonable similarity between these two kind of words? Because, see, whatever we have been talking so far is all about cooperance. How many times they co-appear, and we are trying to calculate either PMI, TF-IDF, or the co-occurrence coefficients or whatever. In basic in that sense. But ideally, are we increasing the level of intelligence by applying this kind of methods? So what has been shown by research, yes, if we apply singular value decomposition kind of methods, we can still be able to understand if this kind of words are actually very similar. If you can try this out from a corpus, you just download and do it. You will get the sense. So now let me skip and directly jump into Word2Vec, and I'll end up in Word2Vec. So this is just a motivation. So how words are connected. Okay. So what is Word2Vec? Word2Vec has been proposed by Mikolov in 2013 when he was a PhD student. It was one of his chapters in his thesis. Now, if you download the pre-trained word vectors from the Google website, later on he joined Google, now he is in Facebook. So if you download this and try to see how this looks like, you might end up getting a vector which is something of this similar, this sort. Now the common question comes to human mind is, what is this? What is this all numbers? What is the range of this number? Can I understand? So to answer to those questions is, so these are not human written. So don't worry if you don't understand those numbers, nobody understands, even not Mikolov. Now, second question comes to your mind, can I understand, okay, the dimension 1 represents what? Dimension 2 represents what? Dimension 3 represents what? When we are jumping into a lattice space and we are understanding, just remember the singular value decomposition example I gave, sci-fi movie versus romantic movies. I mean, each dimension is representing one concept. But what are those concepts for Word2Vec? Well, we don't know. So these are learned from the corpus automatically, and that's possibly the beauty of the whole Word2Vec model, because it learns unsupervised way from a bigger corpus. Unsupervised in the sense, we are not explicitly giving any training data. We are just giving a corpus, and in the corpus we know what are the word co-appear, and we are trying to learn the pattern from there. So this is something Word2Vec gives you. So it's okay if you don't understand what is this. Nobody understands. Now, let me show you. Possibly you have seen already, but if you don't, this is something you should look at. So this is how Word2Vec looks like after getting trained in a bigger corpus. So each dot is nothing but a word, and if you just try to zoom in, you can understand how the words co-appear. This is the vector space. Now, if you search for a word, let's say bike, you get a lot of similar words like bicycle, racing, motorcycles, rider, blah blah blah. So if you just zoom in and try to see if the riding, road, train are similar, and so on. You can possibly also try to visualize this using a better projection method for Disney. And in the meantime, it is getting predicted. Let us show the king-queen analogy for better understanding the Word2Vec model. So see, this is the beauty of the model which actually generates. So what is this? This you might come across all the times. So after you apply Word2Vec, your Word2Vec looks like something of this. This is a vector space, and this is the vector space. This is the vector space. Okay, if you make it 2D, it is actually slowly calculating. In the meantime, let us go back. So this is a vector space. Okay. So what is this vector space is all about? So if you see the distance between woman and queen, let's say this is your vector for 0.3 and 0.9 for queen, and this is your vector for 0.3 and 0.4 for woman. And the distance between woman and queen and king and man are very, very similar. And that's the ideal case or the analogy the paper written by Nikolov has been pointed out. So it is still calculating the major dimension. So let us skip it here and let us go back. So this is Word2Vec. Now how did we come up with this? What is the basics of that? So there are two kinds of models. In Word2Vec, you can see the skipgram and continuous bag of word. So let us talk about continuous bag of word in this way. So this is the kind of architecture. We have only 10 minutes to go. Possibly I end up in 5 minutes and 5-minute question. So what we do is it's a very shallow neural network. So what we do, we give a sequence of words. Let's say word 1 to word 5, and then we are trying to capture. Okay, what would be the possible next three words could be predicted if this is the sequence. Okay, so let's say this is my output 1, this is my output 2, and this is my output 3. My context size is 3, and my vocabulary size is 5. So what we are getting here is one set of hidden layers. So the hidden layer is typically lower in dimension. So if you look at this dimension, this is 5, this is 3 here. So you might ask me questions, why 3, why not 4, why not 5, why not 6, why not something else? So see, the basic idea of Word2Vec again inspired from singular parallel decomposition. We have to squeeze the dimension out while we are capturing the co-occurrence pattern. That's why this dimension has to be smaller. So it has to be smaller than 5, the original dimension. Now, if you try and download Word2Vec written, there are a lot of dimensions available, 100, 300, 700. So the typical question people ask me, student when I'm teaching or doing research, see sir, what dimension is good for my problem or my research or my understanding. So the answer to this is, see, it could be 4, it could be 3, it could be 2, it could be 1. So the basic analogy is, if you squeeze it down too much, you lose information. If you keep it 4, you will get more information. So dimension of Word2Vec should be chosen based on the complexity of the task. See, if you are working on a word vectorization, document vectorization problem for document similarity check or document classification, then possibly lower dimension is just fine, because ultimately you are accumulating a lot of words to get the document vector. But if you are working on a complex problem like textual entailment or let's say machine translation, which are linguistically more complex than document classification, then possibly 700 dimension is the ideal one. So the dimension has to play with the information. So how much information you want to give, how much information you want to, go about. So this is simple. Each node is connected with another node in the hidden layer, and hidden layer is connected with the output layer. So these are the kind of weightage. These are the kind of weightage from the input layer to hidden layer. These are the kind of weightage from the hidden layer to output layer. So what Word2Vec does, it learns this weightage from a larger corpus. So you just give a larger corpus input, and then you do a forward and backward move propagation, and try to learn and optimize these weights, and that's your Word2Vec is. So what is your word vector? Finally, you are getting out when you are training this whole network. You are learning all these weights and etc. So what you are getting out from this hidden layer, basically your hidden layer is the word vector, which you are getting as a written word vector and which you will be further using for your purposes. Whatever NLP task you have, I generally talk about all the mathematics, how it is being formulated, etc. But unfortunately, we are out of time, so I have to stop it here. We have 6 minutes to go. Feel free to ask me anything you have in mind.
Yeah, Khushbu, you can unmute yourself and ask. Shivanshi, unmute yourself and ask. Hello.
Yes.
Good evening, sir. Sir, my question is that a human being can, sir, innovate something new. And as you said that artificial intelligence also learn from the interaction of a human and the past information feeded in the